Hi, everybody. I'm sorry you don't see me, but that's the way it is. 5.4, we're doing 5.4 today, which is the definite integral. So here's the story. We learned in geometry how to find the area of a rectangle, how to find the area of a triangle. And so what about, how about finding the area of a parabola, the area of just a weird, shape? We never learned formulas for that. And part of the reason is because there are no formulas for a lot of these weird shapes. But that is the beauty of calculus, because calculus says, hey, we don't have a formula, but we don't care. We're going to figure it out anyway. So if you look here on the left, you see a curve. This is actually a parabola. And we want to find the area of this sort of, is that beige? I don't know what the color is. Underneath the parabola, above the axis, but underneath the parabola. I want to find that area. And there's no like formula for that, not that I know of. So, but what we're going to do is we're going to find the calculus says, hey, we're going to find the area anyway. What we're going to do is we're going to break this guy up into, these little like rectangles. Now this is called left rectangles because the left corner of the rectangle is the part that touches the curve. And here we have the beige ones underneath are left, but if you look at this whole look at the white and beige combined, that's a right rectangle, because the right corner of the rectangle is what touches the curve. And here, the right corner, if you look at this big rectangle all the way up to here, the right corner of the rectangle is what touches the curve. Now, if you notice, in this particular case, it varies from curve to curve, but in this particular case, the left rectangles, if you add up the area, you're going to get a smaller number than the true answer, because it's going to be less, there's all this white space in between, the curve. If you add up all these big rectangles, the bigger rectangles, you're going to get an area that's a little bit bigger than the actual curve. So what we do, but the true area is going to be somewhere in between. At least we're going to have like a boundary of what the true area is. And in fact, what we're going to do is just imagine if you have these rectangles, if you make these rectangles thinner and have more rectangles and make them thinner, they're going to get closer and closer to the actual curve. See, here it's the same curve, but now the rectangles are thinner, so there's a lot less white space, which means still the left one, and left is not always going to be less than right, but in this particular example, the left is just the nature of how this curve rises. The left rectangles are still going to be less than the true area, and the right rectangles are still going to be more than the true area, but the difference is going to decrease and decrease. It's going to get less and less. They're going to get closer and closer to the actual true area. So let's and that's what's gonna happen. So let's and this is called the error bounds for approximation. If f of x is greater than 0 and is either increasing on AB or decreasing on AB, it has to be monotonically increasing or decreasing. Then f of A minus f of B, that's the largest. That's from this point right here. That the y value here and the y value there. Those two y values, I subtract them, and then multiply that times b minus a over n. Now b minus a over n, that's the width. B minus a in this case is 5 minus 1, and n is how many rectangles there are. So b minus a divided by n is just it really is just the width of each rectangle. So if I make that multiplication, that's called the error bound, and we're saying that yes, it's going to be off. My answer, as I've been pointing out, the answer is going to be off, but it's going to be within this bound. This is the most the error is going to be, and of course, as we make the rectangle smaller, the number n becomes bigger, but nonetheless we and the error decreases. The error gets smaller and smaller. Now I want to actually. But I'm doing a whole bunch of theory, and then we'll get to some examples. I'm going to finally get to example 1. But one more thing. If f of x is greater than 0, we're talking about a positive function that's above the x-axis, and it's either increasing or decreasing. It's got to be one or the other. It can't be no flipping around. Then its left and right sums approach the same real number as n goes. In other words, the overage and the underage get closer and closer to the actual curve, that they both get they approach the same real number, and that same real number is going to be the actual area that the actual area. Here I am. I am still here, and I do exist under the curve. Anyway, I gave you a whole lot of theory now. Well, let's just do an example. Let's just look at an example here. So example 1. So we have a function 9 minus 0.25x squared, which this is what it looks like if you graph it. It's an upside down parabola, a frowny face parabola, if you will. So we want to approximate the area under the curve from x equals 2 to x equals 5. So here is x equals 2, here is x equals 5. So we want this area underneath this whole thing. So what we're going to do is we're going to break this up. We're going to decide. Now we could let n be anything, but in this case we're going to let n equal 6, which means we have 1, 2, 3, 4, 5. There are 6 of these rectangles. So there are 6 of the beige ones of the left. Now notice in this case the right ones are smaller than the true answer, and the left ones are going to be greater than the true answer. And that's just the way it is, you know. But we have one answer is going to be smaller than the true answer. The other is going to be greater than the true answer, but the true answer is going to be in between. Anyway, and we want to answer a bunch of questions. We want to calculate L6 and R6. Well, we'll explain what that. I actually kind of glossed over that, but I'll explain what that means in this. A lot of this, by the way, I just went through a few pages of textbook and I kind of glossed over a lot of stuff. So I think it just makes more sense when we do it in context of an example. And we want to find the error bounds, and we want to know how thin how many rectangles should I make, and how thin in order to get within 0.05 of the true value. For some reason, that's what I need. I need to be within 0.05 of the real value. So what do I got to do to make that happen? That's really the question we're talking about here. All right. So let's start at the very beginning. Okay. So delta x being the width of the rectangles is 0.5. How do you know that? Because if I take 5 minus 2, it gives me 3. You notice from 2 to 5 is 3. There's 6 rectangles I'm breaking it up into, and 3 divided by 6 is 0.5. It's pretty, I mean, there's a formula b minus a over n, but it just means, well, it just means that I explained. So we just graphed it. We drew all the rectangles. So these are the in this case, like I said, the right rectangles are the beige ones, and the left rectangles are the taller ones. Now L6 means the sum of all of the 6 left-handed or left side or whatever you call it rectangles, and R6 means the sum of the 6 right rectangles. So we have the left rectangles and the right rectangles. Now, to get L6, I take f of 2, which is that starting value, times delta x. And because the rectangle starts it here and goes up to that point, which is f of 2. And then the next rectangle has a height of f of 2.5, whatever that number is, times delta x again. The delta x never changes. And then the next rectangle has a height of f of 3 and f of 4, f of 5, and so on. F of 2, 2.5, 3, 3.5, 4, 4.5, and that's it. That's the last of the left rectangles. And right rectangles, instead of starting at 2, I started at 2.5 because the beige rectangle, which is in this case the right one, it doesn't hit the curve at f of 2. It only hits it over here at f of 2.5. So I stagger it, f of 2.5, f of 3, and instead of stopping at f of 4.5, it stops at f of 5. That's what happens. So the error bounds for L6 and R6 is f of 5 minus f of 2 times 5 minus 2 over 6, which is 2.75 minus 2.8 times 0.5, which is 2.6, which means that's the most error can be. And what I want to say here is, I'm sorry, I actually jumped a little bit. How do we get the number 18.5? Well, we took the number 2 and we plugged it into the function, and the function was 9 minus 0.25x squared. And here we took the 2.5, we plugged that into that same quadratic, and we took 3.5, 4. We just took those numbers, plugged them into this original formula, right? This original equation for the curve, 9 minus 0.25x squared, and we got all that. We added it all up. We got 18.53. When we did it on the other, when we did the right ones are the small. In this case, the right ones are the beige ones that are smaller. We got 15.91, and so we got now, which means the answer, the correct answer, the true area under this parabola is somewhere between 15.91 and 18.53, which is not so horrible. That's it's not such a horrible approximation. And of course, notice that if I take 18.53, which was my bigger answer, and I subtract 15.91, which is my smaller answer, I get 2.62, which is what we got from the error bound. So so the error bound, I didn't have to figure out, or I didn't have to add up all these rectangles. I was just able to make a fast approximation. But when I added up the rectangles, I see that the error bound has to be somewhere in that range. That's kind of interesting. It's kind of cool. Okay, and finally, we want to find a large enough value of n where I know it's going to be less than 0.5 of an error. So, which means, because I want to make as many rectangles as I need. Because how many rectangles should you make? Well, it depends on how much accuracy you need. If this is enough accuracy, then it's like it's like anything else. If I want to build something, so how precise do my measurements have to be? Well, if it's a pretty rough, handmade wooden something, so I can be off by a few quarter of inches or whatever. But if I'm building something for a spaceship, and if I'm off by a fraction of a 0.01 decimal, whatever, I can wind up missing the moon. You know what I'm saying? So to the level of accuracy really depends on, and I'm just talking about, that's engineering, but it could be, like I say, it could be something in business, could be something, whatever. Sometimes the level of accuracy makes a huge difference. Sometimes it's not worth, sometimes it does make that big of a difference, and you gotta, at least, so now, is it what's worth it? That's, I don't know, but you gotta at least know what the numbers are. Anyway, I'm talking a lot, let's just go on. So you want to find the value of n that's going to make the error less than 0.5. So I'm going to do f of b minus f of a times b minus a over n. That's the formula for the error. I want to set that to be less than 0.5. Now I plug in 2.75 minus 8, because that's what f of 5 is, and this is what f of 2 is, over 3. That's 5 minus 2 divided by n. And now I want to just solve this for n. So I have the absolute. So I have the absolute value of negative 5.25 times 3 over n is less than 0.05. And then, of course, when I do this multiplication and bring these over and then divide and blah, 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 and solve for n, and this whole thing, I get n is greater than or equal to, well, it comes out to be 315. So if I make at least 315 rectangles, then I will get the accuracy. I will get the accuracy that I require, that I desire. Now, I'm not saying, again, this is all done with computers. You don't necessarily have to see. We're drawing rectangles to kind of give you an idea of what's going on. When you're actually doing this stuff, you don't necessarily have to draw. I mean, in real life, you wouldn't necessarily have to draw these rectangles. Okay, next. The definite integral as a limit of sums. So here's the thing. So if I take the ln, which is the sum of all these little thingy things. So I have, now what's x0, x1? I'm breaking up the these are the, I guess, I don't know how to say it, partition numbers, but I don't want to use the word partition because we use that in a different context. I think this picture here kind of describes it. So x0 is my endpoint A. Xn, which in this case n equals 4, is my endpoint B. And then x1, x2, and x3, those are the that's where the rectangle, that's where the bases of the rectangles, the corners of the rectangles sort of hit the x-axis. Now here I have C1, C2, C3, and C4. What are they? C, if I look at the point where the top of the rectangle hits the curve and goes straight down, that point is C1. I'm calling that C1. And this point here I'm calling C2, and that point there I'm calling C3. The point where the x value, where the rectangle hits the curve. And in this situation, these are the C values. So let's just go back to where we were. Let's go back to the previous page and see how this all plays out. So the left sum is the sum of all the left rectangles. The right sum is the sum of all the right rectangles. Now the sum called the Riemann sum, which is the rectangles that I get, which is the values I get when I take those rectangles that kind of, see, if you notice, again, I just want to point out, in this picture, these rectangles, originally when we started this, we were talking about rectangles where the corner of the rectangle hit the curve. Now I'm talking about where the middle of the rectangle hits the curve. And again, I think that gives us a more accurate answer, because there are parts where there's parts where it's over, parts where it's under, parts where it's over, parts where it's under. You know, so I think the overs and the unders kind of cancel each other out to a certain extent, and it gives you more. And that's really interesting, a whole different thing of finding the best, most accurate thing. And again, it's well, I'm only giving you, in this class, which is just kind of giving you a taste of it. You can spend a lot of time just going through different types of ways. Believe it or not, making little parabolas. It's hard to explain, but this is a really interesting thing, finding the most accurate place to make the rectangles. So okay, well, here's our Riemann sums, and we want to look at the function f of x is equal to 15 minus x squared. Again, it's an upside down parabola, and we're looking at the interval from 1 to 5. So we're going to partition the interval into 4 subintervals, and that's easy because each one's going to be 1 unit wide. Delta x will be 1, 5 minus 1 divided by 4. And the sum now is going to be f of c1 times delta x, f of c2, and so on and so forth. And now, now these C1, C2, C3s, I see, they're really wonderful, but how do I know what the values are? Well, what we're saying here is calculated by just taking the midpoint. So if there's a midpoint between 1 and 2 is 1.5, the midpoint between 2 and 3 is 2.5, 3.54, etc. And now I just add these all up and I get 19. And 19 is the value I get using this method. So it's kind of, as I said, it's still a little bit more accurate than the left and right, because some of the underage and the overage kind of cancels each other out. So it works out really good. And we have a theorem here that the limit of Riemann sums, if f is a continuous function on AB, then the Riemann sums approach the real number limit I as n goes to infinity. And again, that real number that they approach will be the area under the curve. Will be very accurate, for the area under the curve. And that is fabulous. I'm actually going to stop here. I'm going to make a part 2 for the next thing. And actually, hold on 1 second before I do that. So I'm going to actually make a part 1, part 2 on this. Part 1 was all about the crunching, adding up these Riemann sum things and these rectangles, left sum, right sum, Riemann sum, etc. And part 2 is just going to be something called the definite integral. We looked at indefinite integrals, which was just the antiderivative. Now we're going to look at something different called definite integrals, and some properties of how that works. So I hope you're as excited about it as I am. I'm going to make a part 2 to this video, and because that my friend is a story. I will see you guys next time in part 2. See you guys in part 2.